Welcome back. This will be the second part of our video lectures on section 1.1 from the book, covering the geometry and algebra of vectors. If you remember, in the first part of this lecture, we covered vectors in the plane, new vectors from old, and vectors in R3 and Rn in general. And today we'll take up the very interesting and important topics of linear combinations and coordinates, and binary vectors and modular arithmetic. So let's begin with linear combinations and coordinates. The concept of a linear combination is one of the most important things that we will talk about this semester. So let's give a careful definition of what is a linear combination. So a vector u is called a linear combination of the vectors u sub 1 through u sub k, provided that u can be written as a sum of scalar multiples of the vectors u1 through u sub k. Now I think it's helpful to have an image in your mind of a linear combination. What is a way to think about a linear combination? So here's one way to think about it. Think of the vectors u1 through u sub k as permissible direction vectors. So you're allowed to direct somebody from the origin to another point in space, but you can only use the directions u1 through uk. Those are the only things that are allowed. Now, what are you allowed to do with the vectors u1 through uk? You can scale them, so you can stretch them or shrink them, flip their directions, and you can use vector addition, so kind of tip to tail vector addition, but using only those vectors u1 through uk, scalings of them, and vector addition. Can you direct somebody to another point in space? Now, if I hand you a vector u, and you can direct me to the tip of that vector using the vectors u1 through uk and their scalings, then we think of that vector u as a linear combination of those vectors. But if I give you a vector u and you cannot write it in this form, you cannot express it in this form, then that means that I cannot use those direction vectors to direct you to that point in space. So we can think of a linear combination as just a set of directions, right, using the permissible direction vectors u1 through uk, and the linear combinations that we can create from those vectors are the points that we can reach in space using only those direction vectors. All right? Now, what we're going to do is we'll work a series of problems, and by the time we're done working these problems, hopefully you'll have a full sense of how linear combinations work. So let's go to the document camera and let's work on these three problems. All right, welcome back to the document camera. Let's take a look at these three problems. The first problem asks us to show that this vector in the plane can be expressed as a linear combination of these two vectors. So we somehow have to show that there are scalar multiples. Let's call them a and b, such that a times this vector plus b times that vector together gets us to this vector. All right, now I don't have enough room to work this problem on this piece of paper, so I'm going to transcribe this information to a clean sheet and we'll work that problem one out here on a separate sheet of paper. All right, so what we have is we have to show that if I take a, let's use that as our scalar, a times the vector, 2, 1, and you'll notice I'm using columns here because I think that actually helps us see through this problem a little bit better. So I'm going to write these vectors as columns. So a times that vector plus b times this second vector, which is 3, common negative 4. We have to show that there is a choice of a and b such that that can be set equal to 16, common negative 14. So we have to show that this can be done. Now, what we're going to do is work on this left-hand side and simplify it a little bit. We're going to bring these pieces together. Now, I'm going to do this in a couple of steps. You can probably do it in one step, but let me just show you just to make sure that we don't lose anything along the way. My first step is going to be to bring the scalars inside, so do scalar multiplication. So this is equivalent to saying that 2a, a plus 3b, negative 4b, is equal to 16, negative 14. Now that's equivalent by doing component-wise addition. That's equivalent to saying the vector on the left with first component 2a plus 3b and second component a minus 4b is equal to the vector with components 16 and negative 14. But now we use our definition of vector equality. What does it mean to say that these two vectors are equal? It means that component-wise they're equal. So this first component must equal that first component. This second component must equal this second component. So what we're looking for are a's and b's that simultaneously satisfy the equation 2a plus 3b equals 16 and a minus 4b equals negative 14. And I'm going to put this brace here to indicate that we're looking for simultaneous solutions. So we want an a and a b that satisfy this equation and this equation. Now, we're going to have a lot to say about solving simultaneous systems of equations. In fact, that's going to be a major part of this course. But for now, let's just remember we have a couple of techniques at our disposal. This is a simple two equations and two unknowns, so we can kind of hack our way through this. An easy way to solve a system like this is just to match a pair of coefficients and then subtract the equations. In this case, it's very easy just to multiply through on this second equation by 2. Just multiply both sides by 2 and replace this equation by an equivalent equation, namely 2a minus 8b equals negative 28. Now let's think of this as equation 1 and this one as equation 2. We'll temporarily just imagine kind of forgetting about that one. We've replaced it by something equivalent. Now if I take equation 1 and I subtract equation 2, and I do that on both sides of this equality here, if I take equation 1 minus equation 2, because the two a's are matching up, when I subtract them, the a will be eliminated, and I'll get 3b, and be careful here, 3b minus a negative 8b. That's actually 3b plus 8b, so that's 11b on this side. And on this side, I'll have 16 minus a minus 28, 16 plus 28, that's 44. And we can see that 11b equals 44 implies b is equal to 4. So we've been able to find one of our scalars using this process of elimination. Now, in order to find the other one, all you have to do is pick any one of these three equations, plug in the value of b, and solve for the value of a. Well, this middle one, the one that I've actually crossed out, is the easiest one to work with because it's already just got a sitting there all by itself. So we just simply have to plug in a. We're going to get a minus 4 times 4. That's our known value of b. And set that equal to negative 14. Okay? Now that's a minus 16 equals 14, or a equals 16 minus 14 equals 2. So a equals 2. Okay, so now we have our value for the scalar a, and we have our value for the scalar b. And just to reiterate what we're doing here, what we're saying is that the vector 16, negative 14, can now be represented as 2 times the vector 2, 1, and 4 times the vector 3, negative 4. Okay, so this vector here is a linear combination of the vectors 2, 1, and 3, negative 4. So if we think of 2, 1, and 3, negative 4 as our permissible directions, we can direct somebody to this vector using these two direction vectors. We would say take 2 of these and then follow it up by 4 of these, and that will get us, that's our recipe to get us to the tip of this vector at 16, negative 14. Okay, so the idea here is we're trying to reinforce the idea of how to show that something's a linear combination, and then how to talk about it. So we'd say that this vector is a linear combination of these two. Okay, so I hope that helps you understand how to do problem 1. Let's take a look at problem 2. All right, now in problem 2, we have to show that the vector 6, 3, 2 is not a linear combination of the vectors 1, 0, 1 and 1, 1, 0. In other words, we have to show that no matter what scalars we would choose, there's no a and b to use as scalars to make a linear combination of these two vectors ever meet 6, 3, 2. All right, so we have to show that in some sense that this is inconsistent. All right, now again, I'll have to transfer some information to a separate sheet of paper and work it out there, but I'll set it up exactly the same way. I'm going to turn everything into column vectors because I think it's easier to see what's going on. And let's take a look at this situation here. So we want to show that if we look at the system that's embedded here, we're going to be looking at 6, 3, 2. We're wondering if we can choose scalars A and B that would help us solve this equation here. Can we choose scalars so that this linear combination of these two vectors gets us to this vector 6, 3, 2? Do there exist an A and a B? All right, now as before, we're going to do a couple of steps here. We're going to first scale these vectors, and then we'll add the vectors together. So the scalars are going to come in and produce vectors A0A and BB0. And then when I add them together, I'm going to get component-wise addition. I'll get A plus B, 0 plus B, and A plus 0. And we're wondering, can I find an A and a B that produce 6, 3, 2? Now, this turns out again by comparing component by component. If these are equal to each other, they're equal component-wise. So this is equivalent to seeing if there is a simultaneous solution to this system of equations, namely A plus B equals 6, B equals 3, and A equals 2. Can I find simultaneous solutions to this system of equations? Now, this system of equations is very easy because these variables are not very well mixed. Even though I've got 3 equations, they're not mixed very well, especially here in equations 2 and 3. Immediately we can see, for example, here in equation 3 that A must equal 2, and we can see that B must equal 3, and we can see that since A must equal 2 and B must equal 3, here in equation 1, we would reach the absurd conclusion that 3 plus 2 is equal to 6, which is false. Right? That's not true. So there is no choice of A and B. We're forced by equations 2 and 3 to set A equal to 2 and B equal to 3, and this makes equation 1 unsolvable, right? 3 plus 2 does not equal 6. Okay, so in fact, there is no solution. Our system is what's called inconsistent. Okay, and what that means is that if I'm only allowed to use combinations of 1, 0, 1 and 1, 1, 0, here's a vector, namely 6, 3, 2. Here's a vector that I cannot reach. I can't get there using only these 2 direction vectors. Okay, so just because you're given 2 direction vectors doesn't mean, especially here in R3, I'm given 2 vectors in R3, that doesn't mean I can reach some specified third vector. All right, sometimes I can and sometimes I can't. And so here's a good example to show you that there's a really interesting problem here. Given 2 vectors, what vectors can I reach? Well, here's one that I cannot reach. Which ones can I reach? Well, how would I classify the ones that I can reach using only 1, 0, 1 and 1, 1, 0. We'll have a lot more to say about that problem later. But that's our solution to problem 2, and let's now head over and take a look at problem 3. All right, finally, let's take a look at problem 3. We want to show that the vector 2, 2 can be expressed as a linear combination of the vectors 1, negative 1, negative 1, negative 1, and 2, 0 in more than one way. All right, this is actually going to be our most subtle example, so pay special attention here. So let's go ahead and work out this problem in detail on a separate sheet. I'll transfer the information over here. So the idea is we want to show that if we take a linear combination of 1, negative 1, negative 1, negative 1, and 2, 0, those are our three vectors in our set of vectors. We want to show that we can produce a linear combination of these vectors that will yield the vector 2, 2. And we want to show that this can be done in at least two different ways. In fact, there are infinitely many ways, if there are two ways. But let's see how we can produce two different choices of A, B, and C that will give us a combination of these vectors yielding this fourth vector. All right. Now, again, what we're going to do is we're going to scale, and then we'll add component-wise. Now, we've done this a couple of times, so I think we can kind of cut to the chase here. We can kind of quickly realize that this left-hand side is going to be the vector with two components, namely A minus B plus 2C, and negative A, negative B, and C times 0. So that's just plus 0. I won't bother writing that. And that's going to equal to 2. All right? And this gives us a system of two equations in three unknowns, namely A minus B plus 2C equals 2, and negative A minus B equals 2. Now, one thing we can do is we're being asked to show that there's more than one solution. So one thing we can do is just kind of poke around and just see if we can develop some two different solutions to this system of equations. Or we could approach it more, no pun intended, more systematically. At this point in the course, let's not worry so much about trying to be systematic about this. Let's just see if we can poke around and find a couple of different solutions here. And one easy way to kind of tease these things out is to just kind of set some of the values of A, B, and C equal to 0 and see what that implies about the others. So in this case, let's set C equal to 0. We'll make C equal to 0 one of our choices, and we'll see what that implies about A and B. So if we set C equal to 0, this is going to give us the system of equations that reduces to A minus B equals 2 and minus A minus B equals 2. Now this is two equations and two unknown. We can solve for A and B. If I add these equations together, I'll cancel out the A and I'll end up with, so I'm going to basically take equation 1 and add that to equation 2. That's going to eliminate the A, and I'll get a minus 2B equals 4, or B equals negative 2. And then if B is equal to negative 2, in this first equation, we're going to get A minus a minus 2 equals 2. Well, minus a minus 2 is 2, and there's 2 on both sides. We can cancel that. This is going to force A equal to 0. So one of our solutions could be C equals 0, B equals negative 2, and A equals 0. Let's write that one down over here. So we'll have one choice would be A equals 0, B equals negative 2, and C equals 0. So there's one choice of scalars that we could choose in our linear combination. All right, let's try this again. Let's try setting, in this system of equations, let's try setting B equal to 0 and see what that implies for A and C. So now we're going to set B equal to 0. That's going to be our choice for B. And this system is going to reduce to A plus 2C equals 2, and A minus 0, so minus A, negative A, equals 2. So within the second equation, it degenerates. It only involves A, so we get A equals negative 2. And if A is equal to negative 2, in this first equation, we have negative 2 plus 2C equals 2, or 2C equals 4, or C equals 2. So it looks like another solution is going to be A equals negative 2, B equals 0. That was our initial choice that got the ball rolling. And finally, C equals 2. So I'll call this choice number 1. And I'll call that choice number 2. So there's two different sets of scalars, A, B, and C, that we could use to solve this linear combination problem. In other words, if I wanted to try to direct somebody to the point 2, 2 using these direction vectors, I would have two very, very different ways of directing them to the same point or to the same vector using the same direction vectors. Okay? Now, let's go back to these 3 problems. I'll go back to the sheet that listed these 3 problems. I want to take a look at what we've learned from looking at these 3 different problems. All right, now that we've seen these 3 problems worked out in detail, let's just step back and see what we've learned. In this first problem, we learned that, in fact, we could find some scalars that would allow us to combine these 2 vectors to form this third vector. And what we found is that the choice of scalars was unique. There was only one way to do it, in other words. So if I'm going to use these 2 vectors, if I'm going to combine them to form this third one, there was only one way to do it. There was a choice for A and a choice for B, and that was it. In problem 2, we had to show that there was no choice of scalars that would get us to the vector 6, 3, 2. So we didn't have a unique choice. We had no choice. Okay, so there's no choice of scalars that will do the job. And finally, in problem 3, we were asked to show that I could do it in more than one way. Now, we haven't proved this yet, but it turns out if you can do it in more than one way, you can do it in infinitely many ways. And you can kind of see by the way our solution was evolving, we just picked a couple of choices for one of the variables, and we're able to easily work out solutions. It's going to turn out that if there's more than one way to do it, there's actually infinitely many ways to do this. And so what happens here in case 3 is, not only can we solve this problem with a choice of scalars, we can solve it with infinitely many choices of scalars. So if we think of this as the spanning problem, right? If I give you a set of direction vectors, can you use them to reach some other vector? We have to be open to these 3 possibilities. Possibility 1 is yes, we can get there, but that's a unique way. Possibility number 2 is that no, I can't get there with these direction vectors, right? There's no way to combine these to get to that other vector. And then possibility 3 is that in fact there are infinitely many choices of scalars that will allow me to combine these vectors to get to that other vector. So any of these cases is possible. So the spanning problem can resolve itself into one of these 3 cases. All right, let's go back to the class notes. I want to work this problem with you. We'll work out the details under the document camera, but this is going to introduce us to the idea of relative coordinates. So let U be the vector with components 20 and 5. Let V be the vector with components -10 and 10. And I've got these vectors pictured below here. Let P have the coordinates 10 and 34. We want to express the vector OP as a linear combination of U and V. So let's head over to the document camera, work out the details, and I'll show you how this leads us to the idea of relative coordinates. Okay, welcome back to the document camera. Now we can leverage a lot of the work that we did in that previous problem. We worked with the spanning problem, and that's essentially what we have to do here. We have to show that the vector determined by P, so the vector from the origin to P, the vector with components 10 and 34, can be obtained by scaling, or in fact, forming a linear combination of the vectors U and V. So let's write that out. We want to find A and B. We want to find these scalars. So we want to find A and B such that a times the vector 25 plus b times the vector negative 10, 10 equals the vector with components 10 and 34. In other words, the vector that goes from the origin out to P. Now, we've done this kind of work before. We know that this breaks down into a simultaneous solution or a simultaneous system of equations here. So we're going to have our first equation is going to be 20a minus 10b equals 10. All right, and our second equation is going to be 5a plus 10b is equal to 34. So just as before, the spanning problem boils down to solving a system of equations. Now, in this case, it's pretty easy. We're going to try to eliminate one of the variables, and in this case, we can see that if we add these equations together, the 10b's will drop out. The minus 10b and the plus 10b will drop b out of the equation. So adding equation 1 to equation 2 gives me 25a is equal to 44. And that means that a is equal to 44 divided by 25, which gives me a value of 1.76. So a is equal to 1.76. Now we just have to do a little bit of work here. I can either use this first equation or the second equation. It doesn't matter. I'm going to plug in the value for a and solve for the value of b. Let's go ahead and use the second equation. So we're going to have 5 times 1.76 plus 10b equals 34. And so that says 10b must be equal to 34 minus 5 times 1.76. That's 8.8. And so that says b must be what I get when I take 34 minus 8.8. So 34 minus 8.8 divided by 10 is equal to 2.52. So b is equal to 2.52. Okay, and that's our recipe. It says if we take this vector u, the vector that's given by 25, and I multiply it by 1.76, so I scale it a little bit, and then add to it 2.52 times v. So if I stretch u a little bit and then add 2.52 times v, I'll be able to work my way from the origin out to P. Okay, and that's exactly what the spanning problem is achieving. Now, one of the byproducts of working this problem is we want to talk about what are called relative coordinates. And so what I've done here is I've drawn this set of vectors, and I've given you, in some sense, the kind of graph paper that would result by using u and v as the kind of direction vectors for our graph paper. So it kind of gives us this skewed graph paper. And basically what we're saying is, it says relative to the coordinates u and v, relative to u and v, the coordinates of P can be given by this linear combination, right? It can be given to us by these coefficients, the a and the b. So we can say that the coordinates of P relative, and this is the important part, relative to the vectors u and v are 1.76 and 2.52. Right? That would tell us kind of in this system that's determined by the direction vectors u and v, I can think of this point as sitting at 1.76 comma 2.52, because relative to these direction vectors, that's how far I would go in this direction, and then that's how far I would follow it up by going in this direction. I would go 1.76 u's and 2.52 v's, and that would get me from here to the point P. All right, so we can talk about coordinates of a point relative to, in this case, a set of vectors, u and v, in this kind of goofy graph paper world. All right, now one thing I want to point out before we leave this, I want to mention that since I've listed u first and v second, I'm going to list those coordinates in exactly the same way, because this is the multiple of u, and that's the multiple of v that I use in order to get from the origin out to P. So as I list the vectors, I have to list the coordinates in exactly that same order. All right? So if someone hands you a pair of coordinates in the UV system, you would know how to use them to generate the coordinates of this point in the usual rectangular system. All right, so that's this idea of a linear combination and how we can use a linear combination to, in some sense, talk about relative coordinates. All right, I'll see you back at the class notes. So the last subsection of section 1.1 concerns binary vectors and modular arithmetic. Now, up till now, we've been considering vectors whose components consist entirely of real numbers. And this is not bad. It's not a bad place to start because it allows us to leverage our intuition about two-dimensional and three-dimensional Euclidean space. However, as we'll see by the time we finish this subsection, the concept of vector is much broader than that. We can consider vectors whose components consist of, for example, binary numbers. So my hope is that by the time we finish this subsection, you'll have a much broader perspective on the concept of vector. So let's begin by studying the integers modulo 2. The integers modulo 2, denoted by the symbol that's read Z2, it's a blackboard bold Z with a subscript 2. We just say Z2. It consists of the set 0, 1 together with two operations called plus, or addition, and an asterisk, which denotes multiplication. Now, what's interesting is that these operations of addition and multiplication must be what's called closed. They are closed operation. That means when I take elements of Z2, so in other words, when I take a 0 or a 1, I take a pair of them and I combine them either through addition or I combine them through multiplication, I have to get back something that's in the set 0, 1. So the addition and the multiplication must be closed. I should never see a result of addition in Z2 or multiplication in Z2 that is other than a 0 or a 1. Now, addition and multiplication look normal for a while. So for example, if I take 0 plus 0, I get 0. If I take 0 plus 1, I get 1. 1 plus 0 gives me 1. And here's the tricky one, 1 plus 1. Normally that would take us outside of the set 0, 1, right? 1 plus 1 is 2, but this addition has to stay closed. And so when I take 1 plus 1, it returns 0. Okay, let's look at multiplication. This one actually doesn't behave strangely at all. It just follows the normal rules of integer multiplication. 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. And 1 times 1 is 1. We never violate closure under this multiplication, so it just looks like ordinary multiplication. All right, now, here's the thing to notice, and we're going to work on this when we go to the integers modulo 3. We'll see a deeper connection here. But notice that if we replace 0 with the concept of even and 1 with the concept of odd, then these are the ordinary rules for adding and multiplying even and odd numbers. All right, let's just check out this idea. So in other words, we're thinking of 0, when we see 0, we should read even. And when we see 1, we should read odd. So what is this saying? When it says even plus even is even. Even plus odd is odd. Odd plus even is odd. And odd plus odd is even. And let's look at multiplication. Even times even is even. Even times odd is even. Odd times even is even. And here's the exceptional one, right? Odd times odd is odd. So in other words, these rules here that we're seeing for Z2 are the typical rules for multiplying even and odd numbers or adding even and odd numbers. And this system is often called binary arithmetic. Next, let's study the integers modulo 3. So the integers modulo 3, denoted by z3, consists of the set 0, 1, 2 together with the operations of addition, which was denoted by a plus sign, and multiplication, which is denoted by an asterisk. And as before, these operations of addition and multiplication are what are called closed. So when I take a pair of elements of z3 and either add them together or multiply them together, I must get back in return an element of z3. In other words, a 0, a 1, or a 2. So when you scan the addition tables and multiplication tables for z3, you'll notice that the results are always elements of z3. That's the closure property. Now, rather than memorize these addition tables and multiplication tables, let me show you the secret to building these addition and multiplication tables. Now, the first step is to show how we can assign every integer to a unique residue class modulo 3. Now, it turns out that there are only 3 residue classes modulo 3. They are the class 0, the class 1, and the class 2. And here's how the assignment works. 0 goes into class 0, 1 goes into class 1, 2 goes into class 2. So far, so good, right? And now what you do is you just take that pattern of 0, 1, 2, and you copy and you paste it ad infinitum in both directions. So all you see here across the top is the pattern 0, 1, 2 repeated ad infinitum, okay? And this puts every integer into a unique residue class. It gets assigned to either the class 0, the class 1, or the class 2. Now, let's think about what these residue classes are. There's actually a fairly simple interpretation of these residue classes. Now you'll notice that every number in class 0, numbers like 0, 3, 6, 9, 12, or negative 3, negative 6, negative 9, negative 12, they all have the feature of being divisible by 3. And every number that's in class 1 is 1 more than a number that's divisible by 3. And every number in class 2 is 2 more than a number that's divisible by 3. So if you want to know what residue class a number is in, what you can always do is find the nearest multiple of 3 that's below that number. All right, so find the largest multiple of 3 that's less than the number you have in question, and see if you are 1 away or 2 away from that number. So here's a test for you, right? What residue class is the number 38 in? So pause the video here for a second and imagine what residue class would you put the number 38 in? Okay, let's think about it together. What's the nearest multiple of 3 to 38 that's below 38? Well, it's the number 36. 36 is 12 times 3, and that would put 36 in class 0, 37 in class 1, and 38 would be in residue class 2. Now that we understand how residue classes modulo 3 work, it's actually quite easy to describe addition modulo 3 and multiplication modulo 3. And so the idea is quite simple. If I take a pair of numbers and I want to add them mod 3, I first add them as integers. I look at the result, and then I see what residue class that result sits in, and I report the residue class. So for example, let's take a look at some examples of addition first. If I want to add 1 plus 1, I first add them as integers, so 1 plus 1 is 2. And then I see that the number 2 sits in residue class 2. And so I simply say 1 plus 1 is 2 modulo 3. On the other hand, 1 plus 2, 1 plus 2, 1 plus 2 is 3 under ordinary integer arithmetic, so 1 plus 2 is 3, but 3 sits in residue class 0, so I report the answer as 0. 1 plus 2 is 0 mod 3. Here's another surprising one, right? 2 plus 2. 2 plus 2 is 4, but 4 sits in residue class 1, so 2 plus 2 is 1 modulo 3. The same rule applies for multiplication. First, multiply the numbers as ordinary integers, and then report the residue class. So for example, 2 times 2 is 4, and since 4 sits in residue class 1, I report 2 times 2 is equal to 1 modulo 3. Now, if you've understood how to compute these residue classes modulo 3, and if you've understood how to use these residue classes to form the addition and multiplication tables for Z3, there should be no problem adapting this to, say, for example, Z4. When we want to work in Z4, we have to understand that there are going to be 4 residue classes, 0, 1, 2, and 3. And we have to take each integer and put it into one of those 4 residue classes. And as before, we put 0 into class 0, 1 into class 1, 2 into class 2, and 3 into class 3. And this gives us this pattern of 0, 1, 2, 3 that we then copy and paste ad infinitum in both directions. And the interpretation is just as we saw before. To be in class 0 means that you're divisible by 4. And to be in class 1 means that you're 1 more than a number that's divisible by 4. And to be in class 2 means you're 2 more than a number that's divisible by 4. And finally, to be in class 3 means you're 3 more than a number that's divisible by 4. So once we understand that, then all of our calculations in Z4 can be done quite easily. So for example, here's a little problem for us. What's 3 times 3 in Z4? So if you want to, pause the video here and ask yourself, how would I compute 3 times 3 in Z4? Well, in order to do that calculation, we're just going to multiply 3 times 3 as normal integers, right? So 3 times 3 is 9. And what is 9? It's 1 more than 8. 8 is divisible by 4, so we know that 8 is in class 0, and that puts 9 in class 1. And that tells us that 3 times 3 in Z4 will appear in our multiplication table as 1. 3 times 3 is equal to 1 in Z4. Okay, now what I want to do is work with this modular arithmetic a little bit. I've got some problems worked out for us. The first problem for us is to work out some problems in Z2 and in Z3 using both addition and multiplication. And here, the thing we have to do is just respect the parentheses and carry out these operations in a natural way. And then I've got some problems for us to work in Z5 and Z6. So join me at the document camera. We'll work out this problem. All right, welcome to the document camera. We're going to work out a couple of calculations here, one in Z2 and another one in Z3. So let's work out this one in Z2 first. And we have to respect these parentheses. And so what we're going to do is we're going to work from the innermost parentheses out. So we're just going to hack away at this one piece at a time. So let's take a look at this piece. This first parentheses here, inside there we have 1 plus 0. Well, in Z2, that's just 1. So this first expression just becomes 1 plus 0 times, that gets replaced by 1, and we have that finishing parentheses there. Plus 1 times, well, 0 plus 1 is just 1 in Z2, so we have 1 times 1. Let's keep going. Here we've got 0 times 1, which is going to be 0, and so this is just 1 plus 0, or 1. And this is 1 times 1, which is 1. So this is 1 plus 1. But in Z2, 1 plus 1 would be 2. And that's the ordinary arithmetic of 1 plus 1. But in Z2, we have to realize that that's in residue class 0. So 1 plus 1 is 0. And this, of course, is a calculation that's done in Z2. Okay? So this whole thing reduces down to simply 0. Okay. Now, the next calculation. We're doing this one in Z3, so we have to set our minds in terms of calculating in Z3. And again, let's work on these innermost parentheses first. Here we've got 1 plus 0. That's just simply 1. So this first part is going to be 2 times 1 plus, that gets replaced by 1. Okay, this one is going to be 2 plus 1, which is ordinarily 3, but in Z3 that gets reduced to 0. So this is going to be 1 times 0, so that's that part there. And then we have plus 2 times, 1 times 2 in Z3 is going to be 2. Okay, so we've got that. Now let's work on some of these interior multiplications and interior additions. The 1 plus 1 is going to be 2, so this is going to be reduced to 2 times 2. The 1 times 0 is going to be 0. and the 2 times 2 is going to be 4 in ordinary multiplication, but in Z3 that'll get treated as a 1. It's in residue class 1. Okay, now the 2 times 2 in Z3, the 2 times 2 ordinarily multiplies to 4, so in Z3 that's going to get treated as a 1. And the 1 plus, or the 0 plus 1 is going to be 1 in Z3. And then finally the 1 plus 1 will equal 2. And this arithmetic is all being done in Z3. All right, so our first calculation reduces to 1, and our second calculation reduces to 2. All right, I hope that was helpful. It gives you some insight in how to work with Z2 and Z3. Okay, now I want us to work a couple of problems in this case in Z11 and in Z34. So we're going to compute 7 times 6 in Z11, and we'll compute 15 times 11 in Z34. So join me at the document camera and I'll show you how we can carry out these calculations. All right, welcome back to the document camera. We're going to do a couple of calculations, a couple of products. 7 times 6 in Z11 and 15 times 11 in Z34. So let's take a look at this one first. Of course, the first thing we're going to want to do is calculate 7 times 6. That's, of course, very easy. 7 times 6 is 42. Now, what we have to do is we have to figure out what is the nearest multiple of 11 within 42 that gets us as close to 42 as we can without going over. And so if we think of the multiples of 11, we have 11, 22, 33, and then 44. So clearly it's going to be 33. So we can think of 42 as 3 11s. That gets us to 33, plus a remainder, and that's going to be the residue. It's that part that's left over. It's the part that takes us from 33 up to 42. And in this case, that number is 9. And so that's our residue. And so we know that 7 times 6, if we looked in the multiplication table for 7 times 6, we would see that that's equal to 9 in Z11 arithmetic. Okay? Now that you have that idea, you can pause this video and try 15 times 11 yourself. So give that a try. But let's do it now. We're going to do 15 times 11. So if we do 15 times 11 in Z34, the first thing to do is to just calculate 15 times 11 as integers. And so when we do that, we'll get 15 times 11 in ordinary integer arithmetic is going to be 150 plus another 15, 165. Okay? Now, our multiples of 34 are not going to be as easy to count as our multiples of 11. So let's see, 165, we might guess that there are 5 34s in there. So if we do 5 times 34, I'm getting 170. That's too big. So clearly it's 4 times 34. So this is 4 34s. And now we need to know what that remainder is. Well, 4 times 34 is 136. Excuse me. And if I take 136, if I take that away from 165, I get a remainder of 29. So this number 165, well, 15 times 11, 165 is 29 steps past the nearest multiple of 34. So that's our residue. And so we would report that 15 times 11 is equal to 29. That's what would appear in the multiplication table in Z34. So I hope that these couple of problems have given you some insight in how to do multiplication calculations. In this case, in Z11 and Z34, you have the general idea. You can now work mod k for any k. All right, let's go back to the class notes. In this next problem, I want us to explore solving equations, in this case in Z5 or Z6. So join me at the document camera and we'll work out some methods for solving equations like this. All right, welcome back to the document camera. We're going to be solving equations in Z5 and Z6. This method I'm going to show you is not a robust method. There are better methods for doing this, but it will show us how to at least begin to think about solving equations. Let's take a look at this first problem. We want to find the solutions to 2x equals 3 in Z5. So here's one way to do it. I'm going to list the elements of Z5. I'm going to make a little tree here. I'm going to list the elements of Z5. So there's 0, 1, 2, 3, and 4. And underneath that, I'm going to find all the multiplications where I do 2 times that number. So 2 times 0 is 0. 2 times 1 is 2. 2 times 2 is 4. Now we have to be careful. We're in Z5. So when I do 2 times 3, I'm going to get 6. That's in residue class 1. And then 2 times 4 is 8, which puts it in residue class 3. So there are the products, 2 times n, where n ranges through the 5 elements of Z5. And now we're looking for the solution to 2x equals 3. And so we can clearly see that that is solved by x equals 4. So x equals 4 is our solution to 2x equals 3 in Z5. Now, there are better ways, there are more robust ways to do this, but just getting started thinking about solving equations, this does the job. Now, let's apply that same technique to solving 3x equals 2 in Z6. If you want to try this on your own, stop the video and try this on your own. That would be a good idea. But let's go ahead and build a tree and see if we can find solutions to 3x equals 2 in Z6. So there are going to be 5 elements in Z6, and they're going to be 0, 1, 2, 3, 4, and 5. And when I look at 3 times these elements, I'm going to get 3 times 0 is 0. 3 times 1 is 3. 3 times 2 is 6, but in Z6, 6 is in residue class 0. 3 times 3 is 9, and that puts it in residue class 3. 3 times 4 is 12, and that is in residue class 0. And 3 times 5 is 15, and that's going to be in residue class 3. That's going to be 12 plus 3, so this will be 3. So we see that in Z6, when I multiply by 3, the only outputs that I ever see are 0 and 3. So that's the only thing that will ever come out of a product of 3 times x in Z6. And that means that 3x equals 2 has no solutions in Z6. All right, so that's interesting to note that something as simple as 3x equals 2 can have no solution in Z6. Now, let's apply exactly the same technique to solving 4x equals 2 in Z6. So I'll make a tree here. This time I'm multiplying by 4. So we'll do all our products times 4 in Z6. So we're going to have 4 times 0 is 0. 4 times 1 is 4. 4 times 2 is 8. In Z6, that's residue class 2. 4 times 3 is 12. In Z6, that's going to be 0. 4 times 4 is 16. And in residue class 6, 16 is going to be 4. That's going to be 12 plus 4. So we'll have 4. And then 4 times 5 is 20, and in residue class 6, 20 is going to be in residue class 2, because it's going to be 18 plus 2. So this will be 2. So we see this nice pattern, 0, 4, 2, 0, 4, 2. All right. Are there any solutions to 4x equals 2? Well, unlike the previous case, here we actually find more than one solution, right? We can see that 4x equals 2 will be satisfied for both x equals 2 and x equals 5. So in this case, we have 2 solutions, x equals 2 and x equals 5. Okay, so what we can expect, this kind of shows us what we can expect when we're solving equations in z sub k, right? We might have a unique solution, we might have no solution, and we might have more than one solution. So a lot of things are possible when we're working with equations in z sub k. So I hope you found that interesting and illuminating. And if you want to study this in greater detail, you can pick up a book on number theory and you can look at these kinds of equations. All right, let's go back to the course notes. So now that we've studied integer arithmetic modulo k, or working in z sub k, we're now prepared to study vectors whose entries come from z sub k. So the set of vectors of length n of the form u equals u1, u2 up through un, all of whose components come from zk, is denoted by z sub k superscript n. So that's a mouthful, but what this is telling us, the way we should read this is first we read zk. That tells us the entries are coming from zk, and the superscript is telling us the length of the vector or the dimension of the vector. Now, adding vectors of this form is going to be easy because vector addition is component-wise, and so we know that we can add component-wise as elements of zk. We have to be a little bit careful with scalar multiplication. In order for scalar multiplication to make sense, we have to make sure that our scalars come from zk. That way, all of the component-wise multiplication by that scalar will make sense in zk. All right, so what I want to do, and hopefully this will make sense once we work this next problem, what I want us to do is just work out some scaling and vector addition. In our first problem, we're going to be working in z5 superscript 4, so that we're going to be working in vectors of length 4, all of whose elements come from z5. And in our second problem, we'll be working in vectors of length 5, whose elements come from z4. All right, so join me at the document camera. This will be our last problem and our last element for this section 1.1. So join me over there. We'll work this out, and that will close off section 1.1. All right, welcome to the document camera. Let's work this problem together. And we're going to do the scalar multiplications first, and then we'll do the vector addition second. And the only thing we want to make sure we pay attention to is the fact that we're working in Z5. So all of our calculations, our multiplications and our additions should be done in the Z5 sense. So let's see, in this first scalar multiplication, we're going to have 3 times 1, which in Z5 will be 3. 3 times 0 is 0. Now 3 times 2 is 6, but in Z5 that's going to be in residue class 1. And 3 times 3 is 9, and that's going to be in residue class 4. So this first vector will be 3, 0, 1, 4 after we do our scalar multiplication. In the second vector, we're going to have 2 times 2, which is 4, which will be 4 in Z5. 2 times 3 is 6, that's going to be 1 in Z5. 2 times 1 is 2, and 2 times 1 is 2. So there's our second vector after scalar multiplication. And now we just have to add these together component-wise to get our final result. So let's see, we'll have 3 plus 4 is 7. That will become residue class 2. 0 plus 1 is 1. 1 plus 2 is 3. And 4 plus 2 is 6, which will resolve to residue class 1 in Z5. So our vector, the linear combination of these two vectors, results in a vector with components 2, 1, 3, and 1 in this vector space. All right, let's work the second problem here. Now, we've got vectors now with components coming from Z4, and so we'll just have to do all of our work relative to Z4. Let's do this again. We'll do the scalar multiplications first and the vector addition second. So here's how this first vector is going to look after we do the scalings. We'll have components of 2, 0, 2. Now here's where things get interesting. 2 times 2 is 4, and 4 resolves to 0. That residue class is 0 in Z4. And again, 2 times 2 is 4, so that'll be another 0. So our first vector is going to be 2, 0, 2, 0, 0. Okay. Now we'll have 3 times 0, which is 0. 3 times 1 is 3. 3 times 1 is 3. 3 times 0 is 0. And here's an interesting one. 3 times 3 is 9. And in Z4, 9 is 1 more than 8, so this will be residue class 1. All right, now we just do our additions in the Z4 sense. Okay, let's see what we get. 2 and 0 give me a 2. 0 and 3 give me a 3. 2 and 3 are 5, and 5 is residue class 1. Okay, 0 and 0 are 0. And then finally 0 and 1 gives me a 1, residue class 1. So our final vector here in this vector space is going to be 2, 3, 1, 0, 1. And that's how we do basic vector operations over Z5 or Z4. And in general, you could see how to extend this to any Z sub k. All right, so that brings a close to section 1.1. So I will see you again in a video lecture where we begin to study the topics in section 1.2. Until then, take care of yourself. Bye-bye.